Was it 10 point? I'm a little bit confused. Like when doing the math that we had to do for this one, that's another R dot. So that's my experimental one. I don't remember. It's
You
like,
just gotta find the half-life. And then you gotta find the scenario.
it's the no. I guess that's what I'm asking. I don't know what the theoretical value is. Because I have the experimental value.
Oh, yeah.
How do I Google that? Like,
We did like KA when someone the natural word KA. KA is not 55. So your percentage is a little bit above.
and then you divide it by 10.34.
By that by the true.
Finally.
Yeah. That is true. Experimental minus true divided by true times. It'd be like what? 10% or something. I think also said 10, 12%.
Right. So I did this and I printed it off and I turned it in. Like I slipped it under his door. I slipped it under the wrong door. So now I just have to redo it. So I know. And then I forgot what number we used.
Can the people on Zoom hear me?
Yes.
Yes.
The people in Zoom hear me at all?
Yes, we can hear you.
So you can hear me, okay. So for some reason, the projector is not working. And I don't know why. So that's your reward for coming to class is you can't.
Or if it comes down to we can follow along on photos.
Or did you use?
Or if it comes down to we can just.
Can you pull it up? Okay, sorry about that. All right. We're going to go ahead and get started. And sorry about late here. We're having some projector problems in the room. Okay, so what we're going to do today is we're going to go ahead and we're going to review the answers for the quiz that we took right before the break. And then after that, we'll go ahead and we'll continue on with the acid-base equilibria chapter, which we started right before spring break. So welcome back from break. Hope everyone had a nice week away from school. And we'll go ahead and get started. So first question, the equilibrium constant expression depends on, and the answer is stoichiometry of the reaction. So those coefficients that are in the reaction tell us what power to make the different concentrations squared or anything like that. Number two, which of the following expressions is the correct equilibrium constant expression for the reaction below? The key there was to remember it's products over reactants. And then if it's a pure solid or pure liquid, it counts as one, so it doesn't show up in the expression. So that leaves us with NH3 squared times H2SE as the correct answer. And number three, acetic acid reacts with ethanol to form ethyl acetate and water. So in this case, it's, as it says here, water is a product rather than a pure liquid, so you needed to include it in the equilibrium expression. And so then we're given the reaction below, and we're also given that the equilibrium constant is 6.68, and we're told 15 liter solution initially contains 0.275 molar acetic acid and 3.85 molar equilibrium, ethanol. So then we wanted to know what's the equilibrium concentration of ethanol. And the answer is 3.58 molar, but how do we get there? Okay, so what we would want to do is, the first thing is look at our equation, okay? And that's the acetic acid plus the ethanol forming the ethyl acetate of water. Then we'd want to write our equilibrium expression. So that's concentration of ethyl acetate times the concentration of water divided by concentration of acetic acid times the concentration of ethanol. All the coefficients are 1, so we don't have to change any of that. And then the next thing to do would be to set up the table that we had talked about previously. So with the table, we have our initial row, we have our change row, and we have our equilibrium row. And then we have our reactants, the acetic acid and the ethanol, and then the ethyl acetate and water for the products. So we started out with 0.275 molar acetic acid and 3.85 molar ethanol, and no ethyl acetate and no water. Then we have some kind of change. Since the reaction stoichiometry is 1 across the board, we know that then for every X of acetic acid that reacts, X of ethanol will react, and then X of ethyl acetate and X of water will be formed. So that's the change that's going to occur. The next thing is then what does that do to our equilibrium? And so 0.275 for the acetic acid minus X, 3.85 minus X for the ethanol, and then X forms of ethyl acetate and water. We go ahead and take those values and put those into our equilibrium equation that we had generated. And so that's X times X in the numerator, and then 0.275 minus X times 3.85 minus X in the denominator. At this point, now it's a matter of doing the algebra. So you can kind of look through this in detail if you want. You can look through in detail on the algebra, but at the end of the day, you wind up with 5.68 X squared minus 27.6X plus 7.08. So if you had some problems with the algebra, I would suggest going back and taking a look at this in a little more detail and try working through it again. That set us up to use the quadratic equation. And so we wanted that AX squared plus BX plus C equals 0 form. So we got things in that form. And then we can go ahead and plug the variables in for A, B, and C into the quadratic equation. Remember with the quadratic equation, you get the plus or minus. So you do the calculation once with that being a plus sign, and then you do it again with it being a negative sign. If you do that for the plus sign version, you get 4.57. And for the negative version, you get 0.272 molar. And so what you have to do here is make a decision on which of these makes sense and which doesn't. Usually with the quadratic, you wind up with one of them doesn't make any sense and the other one does. If we go back and think of what our initial concentrations were, there were 0.275 for the acetic acid and 3.85 for the ethanol. We see that the 4.571 value is bigger than either of those numbers. So that's not realistic. So that tells us that we want to use the 0.272 value. And then, so we have 0.272 for our X value, but we're not finished yet because in the equation, we wanted the molar concentration and equilibrium for ethanol. And we go back to our table. So we go back here and we set an equilibrium for ethanol. It's 3.85 minus X. So what we have to do is we have to take our X value of 0.272 molar and subtract that from the 3.85. And if we do that, we get a value of 3.58 molar for the answer. Okay. So number 4, if the reaction quotient for a reaction is greater than the value of the equilibrium constant for that reaction at a given temperature, what needs to happen? Well, products must be converted to reactants for the system to reach equilibrium. In number 5, consider the following reaction: CO plus 2H2 going to CH3OH. So we're told at equilibrium, the concentrations of CO and H2 were 0.15 and 0.36. And we need to find the equilibrium concentration of CH3OH. And we're also told that the equilibrium constant value is 14.5. So we want to write our equilibrium expression. So that's CH3OH divided by CO times H2, that quantity squared. And then we would want to plug in our values. So 14.5 is the equilibrium constant, and that's equal to the methanol concentration divided by 0.15, the CO concentration, times 0.36 squared, which is the H2 concentration squared, based on our stoichiometry of our reaction. If we do that and then go ahead and solve for the methanol concentration, we get a value of 0.282 or 2.82 times 10 to the -1. Number 6, we're told that N2O4 decomposes to 2 moles of NO2, and we're told that we start with 0.04 moles of N2O4, and then at equilibrium, we're told that 0.0055 moles of N2O4 remains. And we want to calculate the equilibrium constant for this reaction. So as in the previous one, the first thing you do is you write out that equilibrium expression. And so it's NO2, that quantity squared, divided by N2O2. The other thing we need to do is we need to figure out how many moles are involved. So we had 0.0400 moles that we started with. We're left with 0.0055 moles. So if we subtract those numbers, it tells us that we have 0.0345 moles of N2O4 that reacted. So if there's that many moles of that reacted, we know the stoichiometry is 2 to 1. So we multiply that by 2 to tell us how many moles of NO2 formed. So that is 0.0345 times 2 to give us 0.0690 moles of NO2 were formed. It's a 1 liter flask, so we don't have to do any conversions to get into molarity. It's in molarity because that's moles per liter. And we can then plug those two values in, the 0.0690 squared divided by 0.0055 to give us a value of 0.87. Question 7. In an exothermic equilibrium reaction, decreasing the reaction temperature favors the formation of reactants. That is false, because in an exothermic, it's giving off heat. So adding the heat does not help. Which of the following expressions is the correct equilibrium constant expression for CO2 plus 2H2 going to CH3OH? Well, once again, it's products over reactants. So it would be the CH3OH concentration divided by CO2 concentration times the H2 concentration squared. Number 9, we're told that at equilibrium, Kp equals 1.10, and we want to calculate Kc for this PCl5 going to PCl3 plus Cl2 reaction. So there you'd need to remember the formula that we talked about. Kp equals Kc times RT to the delta N. R is the gas constant, T is the temperature in Kelvin. Delta N is that change in moles, products minus reactants, moles of gas. So if we change 250 C to Kelvin, we get 523 Kelvin. The change in moles, product minus reactant, we have 2 moles of gas in the products, 1 in the reactants, so 2 minus 1 is 1. So we know the gas constant is 0.08206. So now we can fill in what the Kp value is, we can fill in the R and T values and the delta N value. And if we go ahead and solve for Kc, we get 0.0256 or 2.56 times 10 to the minus 2. Then the last one, sorry, I didn't advance that. The last one is equilibrium constant, Kp is given, it's 0.121. We have an initial pressure of 0.123 for PCl5 charge. And then we want to calculate out what the partial pressure of PCl5 is in atmospheres. So what we're going to do is we're going to write the equation. It's the same equation that was in number 9. So we had that already, PCl5 going to PCl3 plus Cl2. And we write that equilibrium expression. It's PCl3 times Cl2 concentration divided by PCl5. Then we go ahead and we create the table with our initial, our change in our equilibrium values for the 1 reactant and the 2 products. And so we start out with PCl3 as 0.123 molar and 0 for the 2 products. These is 1:1:1 molar ratios in the reaction. So all those are going to be X. So we have X reacting from PCl5 and X forming for PCl3 and Cl2. That results in the equilibrium being expressed as 0.123 minus X, and then X and X for Cl2. Now that we know the representation for the equilibrium concentrations, we can plug those back into our equilibrium expression. And so that's X times X in the numerator and 0.123 minus X in the denominator. And that's equal to our Kp value of 0.0121. So just as before, we have to do some algebra there. So if you work through the algebra, then you can get to the quadratic equation format of x squared plus 0.0121x minus 1.49 times 10 to the minus 3 equals 0. We plug those coefficients into our formula, solve for plus and minus. The plus version is 0.0330 for x. The minus version is minus 0.0451. So just as on the earlier problem, we have to make a decision. We have to make a decision about which of these makes sense and which doesn't. Well, the 1 is a negative number, so that should tell us that that's not the correct one to use. We want to use the positive number, 0.0330. So we want that equilibrium concentration. So we remember we represented the equilibrium concentration for PCl5 as 0.123 minus X. This value, this 0.0330 value is the X value. So we need to subtract that from the 0.123 to get a value of 0.090. Okay, so any questions about the quiz? Okay. Well, let me go ahead and pull up the slides. Can the people on Zoom see the slide? Okay, thanks. Okay. So we had left off we didn't. It's all right. We had left off last week before the break, before the break, about talking about acids and bases. And so we've made some definitions about what's an acid and what's a base. And so what we're going to do today is continue on that kind of discussion and talk about that. And so the first thing I want to talk about is water. So water can actually act as an acid or base. We talked about that. That means it can accept protons, it can donate protons. And when you have pure water, most of it is sitting around as H2O, but there are a few of the molecules that are H3O plus, and a few of the molecules are OH minus. And so this is referred to as autoionization. And so because water can serve as acid or base, that term we use there is amphoteric. There's a term that we use to express this nature of water, and that's the ion product constant. And so what this really is just the equilibrium expression for water. So just as before, we had products over reactants. That's all this Kw, this ion product constant for water is. So it's H3O plus concentration times the hydroxide concentration, and that's equal to 10 to the minus 14th, 1 times 10 to the minus 14th. And this relationship is one that you'll see we use quite a bit and will continue to use. And so when we do some calculations here in a little bit. And so the other thing I want to point out is you'll see this written as H3O plus times OH minus. And you'll also see it written as H plus times OH minus. Technically, it's H3O plus, but in reality, people usually don't write it that way because they don't want to write it all out. So I'll use those terms interchangeably. Most people do. Like I said, most people just usually say hydrogen ion. But the key to remember is that this ion product constant that we're calling is really just the equilibrium expression, because the denominator on this would be H2O as a pure liquid, and that's 1, so it's not written into the expression. So don't think it's really something new. It really isn't anything new. It's similar to the equilibrium expressions that we talked about before. The key is knowing that this concentration, hydrogen ion times hydroxide ion concentration is equal to 1 times 10 to the minus 14. Okay, so when we talk about aqueous solutions, if the hydrogen ion concentration and the hydroxide ion concentration, if those concentrations are equal, we say the solution is neutral. If the solution has more hydrogen ions, if that concentration is bigger than the hydroxide ions, we say it's acidic. And then if it has more hydroxide ions, so a higher hydroxide concentration than hydrogen ion concentration, then we say that solution is basic. It's nice to talk about the concentrations, but one of the negatives to that is the concentrations are usually pretty low. You see like 10 to the minus 2 or 10 to the minus 10 or something like that. And so as a result of that, people usually, when they talk about acidity or basicity, they use the term pH. I think most people are probably familiar with that term. You hear people talk about it, but let's go into a little more detail on exactly what that means. So pH is just a way to report the hydrogen ion concentration. And so pH is equal to minus the log of the hydrogen ion concentration. Hydrogen ion concentration, hydronium ion concentration, same thing. So rather than use that some number times 10 to the whatever, we often say what the pH is. And so if the pH is 7, that's considered neutral. So the pH is 7, you have the same concentration of hydrogen ions and hydroxide ions. pH below 7 is acidic. So in other words, you have at low pHs, you have more hydrogen ions, that concentration is greater. And pH above 7 is basic. And so that tells us that the hydrogen ion concentration is less than the hydroxide ion concentration. A couple of things about pH. One is that when you look at that pH number, really what it's saying is the number to the left of the decimal is giving us a feel for the power of it. And so for instance, pH of 7 is 1 times 10 to the minus 7th. The numbers to the right of the decimal, in this case, there's 2 of them, that tells us the number in front. So is it like 2.4 times 10 to the something or whatever like that. So those 2 numbers to the right are the significant figures when we talk about logs. This is something that long ago, when people before calculators and computers and all that used to have literally log tables to use. And so this was people were a little more familiar with this. Anymore, most people have forgotten about this because they don't ever have to look things up in the log tables. Lucky for you, I'm old enough that I had to do that, so I remember it. A couple of things I want to point out before we leave this slide, though, is over on the right-hand side, there is some common acids and common bases. And what you'll see here is, I want to point out is, the higher on the left, the higher up it is, the stronger the acid it is. And if you look on the ones that have been identified, you see stomach acid is about 1 times 10 to the minus 1. So that's a pH of 1. That's really acidic. And so if you ever have had like acid reflux or anything like that, and you feel it burning in your esophagus, this is why. It's really very acidic. And that's why people will take Tums or something like that to help neutralize that acid. So stomach acid, very, very low pH, very aggressive acid, very strong acid. You see some others on there. There's lemon juice, cola, vinegar. Vinegar, that's dilute acetic acid. I think you've used that in some of the labs. I know last semester we did a titration with that. And you see some other things listed there. I do want to mention that sometimes you'll see on the internet that if you take a nail or a tooth or something and put it into Coca-Cola, it'll dissolve it. That's completely false. And so, if you don't believe me, try it yourself. But it's not that strong of an acid. On the right-hand side are bases. And so as you go down that list, you get to stronger bases. And we'll talk a little bit in a moment here what we mean by strong acids and bases exactly. But you'll see some household cleaners, ammonia and bleach, are on the stronger end of the base side. And that's why you'll see sometimes with these products, there's warning labels of don't mix certain things together. And that's why, because it's a pretty strong base, and you got to be a little careful with that. You'll hear people talk about base, and you'll hear people use the word caustic. Caustic is another term that's used to describe basic compounds and basic products. So the key takeaway here, pH minus the log of the hydrogen ion concentration, and neutral pH is 7, below 7 is acidic, above 7 is basic. I do want to make a comment about the P. So we talk about pH. So pH itself there's nothing unique about that P function. A P function just means minus the log. So instead of writing out minus the log all the time, you just say P whatever, in this case, pH. But you also can have POH. You can have a pK value. In this case, it's the pK for the water. And what you see here is that POH would be minus the log of the hydroxide concentration. And the pK for water actually is used quite a bit, because what this means is pH plus POH equals pK for water. And remember, the K for water Equilibrium constant for water was 10 to the minus 14th, so minus the log of that would be 14. What that tells us is that pH plus pOH has to add up to 14. So that's why this relationship, this hydrogen ion times hydroxide ion equals 10 to the minus 14, that's important because it allows us to do some things in figuring out pHs and pOHs that we wouldn't be able to do if we didn't know this relationship. So let's just talk a moment about measuring pH. There's a few common ways to do it. The most common way, and the most, at least in a laboratory setting, is to use a pH meter and a pH electrode. I think you've done that in your lab this semester. I think you're doing it right now from what I've heard. And so what you're doing there is the electrode is able to detect small changes in voltage. And if you recall, you should have calibrated that pH electrode and meter so that you defined what a pH was. And then when you have changes off of that, then the meter is able to do a calculation internally that says, okay, if the potential has changed this much, then that means the new measurement is this. So this is an electrochemical type measurement. We'll actually talk about electrochemistry a little later in the semester, but this is a real common electrochemical type measurement that people do all the time in the lab to determine the pH. There are some other ways to determine pH. They're not as accurate and precise, but they're pretty fast and also pretty cheap. One is there are certain chemicals that change color based on the pH. And those are often used as indicators in titrations. And on the list here, if you look at the table in the middle, kind of towards the bottom, you'll see phenolphthalein. And if you recall, we did a titration last semester where we used phenolphthalein as our indicator. So remember, you put the phenolphthalein in and the solution was clear. You started titrating with base. And then as you got to your endpoint, it started changing to a pinkish color. And depending on how good you were, you either had light pink or dark pink or something like that. What you see is that transition for phenolphthalein starts around pH 8 and goes through to about pH 10. So if you had a really, really dark one, you might have been at that pH 10 or 9 type thing. If you had a really light one, you were probably down around pH 8. But so these compounds, and there's a series of them listed here on the slide. But what they do is they have different colors based on the pH, and that kind of gives you a general idea. If you really are trying to get a real accurate, precise pH measurement, this usually isn't good enough. And that's where I believe you guys in your titration that you're doing now, you're using a pH meter to measure the potential and you're then plotting that. And that data really should be better than something you would get with this, because with this, you're dependent upon the person being pretty patient when they're titrating. So different people have different abilities to detect that color change, whatever it is. Whereas with the pH measurement, as long as you calibrated your pH meter correctly, you get all the points. And even if you overshoot it, you just keep taking points and then you plot and you can then figure out endpoints that. Another way to measure pH, which is similar to these indicators, is that there's actually pH test strips. And so these will be, and depending upon how good a one you get, there's different quality of them. But ones that are pretty good have usually 4 different spots on them, and you wet each spot, and then whatever that color combination is, usually have a little reference chart with it, and that tells you what the pH is. And those are usually actually pretty good. And depending upon what you get, you can have fairly precise measurements on that. And so that's another version. A lot of times you'll see those test strips for like people who have swimming pools or aquariums or things like that. But it's similar to this, where you're basing it on color changes of molecules that are known to change at certain pH values. Okay, any questions about any of the pH stuff that we just talked about? Okay, what I'd like to do then is look at a couple of homework problems before we move on. So let me grab that. Okay, so the first one I'd like to look at is 16.17. And so they want you to, we want to identify the Bronsted acid and Bronsted base, and then the conjugate of them. So what, does anyone remember what a Bronsted acid or base, what it has to do or have? So Bronsted acids have to be able to donate a proton, and Bronsted bases have to be able to accept a proton. So for it to be an acid, it's got to have a hydrogen that is donatable. And if it's a base, it's got to be able to accept that hydrogen. So in this case, we have NH4 plus CN minus going to HCN and NH3. So if we look here on the left, between NH4 plus and CN minus, if something's got to be able to donate a proton, well, we don't have a proton on the CN minus, so it can't be that. So then that leaves NH4 plus, in this case, is working as an acid because it can donate that proton to the CN minus to form HCN, and then the NH4 plus becomes NH3. So then the conjugate base to the NH4 plus acid is this NH3 over on the product side. And then the CN minus is the base because it's going to accept the proton, and then its conjugate acid is HCN. So when we're looking at these, this is kind of the approach we take, is we look at things on the left and right, see which ones match up. So in other words, the NH4 has got to go with the NH3. It's not going to go with the HCN or anything like that because it's not the conjugate of it. When I think of conjugate, I just think of something that's going to be real similar. Okay, let's look at two others here. So we have CH3N plus water going to CH3NH and OH minus. So in this case, we might be tempted to think that the CH3 on the nitrogen, that could donate a proton. Well, those protons aren't donatable. And if you didn't know that, which at this stage you may not, an easier way to do it is to look what's on the product side and see, well, what gained a proton? Well, in that case, we see that the three methyl groups on the nitrogen, that actually picked up another hydrogen. So that tells me that I didn't donate a proton out of that CH3N compound. It had to come from the water. And then we see the water, there's an OH on the right-hand side. So from this, we can look and see that it was H2O that donated a proton, that donates a proton, then it's an acid. We see the CH3N picked up a proton. So that's the base. So we've identified the acid and base on the left-hand side, and the conjugates are on the right-hand side. And then finally, the last one is going to be a similar approach where we have HCOOH and then PO4 minus 3. And we look at those two, trying to figure out which is the acid and the base. Well, only one of them has a donatable proton, only has a proton rather. And that's the formic acid, the HCOOH. And that donates to the phosphate, the PO4 minus 3, to form HCOO minus and HPO4 minus 2. So we're able to see the acid is the HCOOH on the left-hand side, the base is the PO4 minus 3, then the conjugates are on the right-hand side. The HCOO minus is the conjugate base for the formic acid, and HPO4 minus 2 is the conjugate acid for the phosphate anion. Okay, any questions about the conjugate acid base stuff? Okay. Let's take a look at 1629. So So in 1629, we want to calculate the hydrogen ion concentration for these solutions and then decide if it's acidic, basic, or neutral. So here's where that relationship, that equilibrium expression for water comes into play. So if we remember that the equilibrium expression for water is hydrogen ion times hydroxide ion equal to 1 times 10 to the minus 14, then we can take the information that we're given and plug it in order to solve for whichever variable we're looking for. So in this case, we're told we have 0.00045 molar hydroxide. And so we need to plug that in and then plug in our 1 times 10 to the minus 14th, and then go ahead and solve for the hydrogen ion concentration. And we get a value of 2.2 times 10 to the minus 11. So if you're like me, I'm more comfortable deciding if something is acidic or basic by having it in pH units. And so if I go ahead and then do minus the log of 2.2 times 10 to the minus 11, I see the pH is 10.7. And 10.7 is greater than 7. So we said if it's greater than 7, it's basic. Okay, in the next one, we're told the hydroxide concentration is 8.8 times 10 to the minus 9 molar. Just as we did previously, we use that water dissociation value, that relationship, plug in the hydroxide, solve for the hydrogen ion concentration. In this case, we get 1.1 times 10 to the minus 6. So if we do and the minus the log of this to find the pH, we see that the pH value is 5.9. 5.9 is less than 7, so we know this is acidic because pH less than 7 is acidic. Okay, so those two were pretty straightforward. We took advantage of that equilibrium of water equal to 10 to the minus 14, plugged in a concentration, solved, found the pH to see if it's acidic or basic. This one's a little bit different. We're told that the hydroxide concentration is 100 times the hydrogen ion concentration. So in that case, we're going to use the same setup of 1 times 10 to the minus 14 equals the hydroxide ion concentration times the hydrogen ion concentration. But we're going to substitute 100 times the hydrogen ion concentration for that hydroxide ion concentration. And when we do that and we do the math, now we have 100 times hydrogen ion concentration squared equals to that 1 times 10 to the minus 14. So we weren't given a number for a hydroxide concentration, but we were given a relationship between hydrogen and hydroxide. And so we leverage that to define it so we only have one variable, which is hydrogen ion concentration. We can go ahead and then solve for hydrogen ion concentration, and we get 1 times 10 to the minus 8. If we take minus the log of that to put that into a pH form, we see that the pH is 8, and so it's a basic solution. Any questions about the homework problems that we looked at? There's a few others you can do. And one that I would ask you to spend some time on, I'm just going to talk about this one briefly. I'm not going to go through all these numbers. But in 1635, we're given some information. And in different parts of the problem, you get different information. But what you see here is you have hydrogen ion concentration, you have hydroxide ion concentration, you have pH, you have pOH, and then you want to know if it's acidic or basic solution. Well, there's 4 relationships that you need to remember to be able to fill in this table. And so let's just talk about what those are. The first is that pH is minus the log of the hydrogen ion concentration, okay? pOH is minus the log of the hydroxide ion concentration. And We also know that pH plus POH is going to equal 14. And then the final thing is that water dissociation constant of hydrogen ion concentration times hydroxide ion concentration equals 1 times 10 to the minus 14. So using some combination of these relationships, you can fill out the pieces in the table. And so for instance, if you're given the hydrogen ion concentration, you can quickly find the pH, okay? So you do minus the log of that value. Now you have a pH. You can get POH pretty easily by subtracting that pH from 14, and now you've got POH. You can get the OH, there's several ways you can do this, but one is, if you've got a hydrogen ion concentration, you know that times the OH concentration is 1 times 10 to the minus 14. So you kind of get a feel for, you know, if you were given the pH, well, then you could find POH pretty quickly. You take the antilogs of those to get the concentrations, and that's at the bottom of this problem I have worked out to remember. If you have it, the pH value or the POH value, and you want to get the concentration, you would do 10 to the minus whatever that number is, pH or POH, okay? So that's one of the things, make sure you know how to do that on your calculator. So for instance, if you had pH of 2.12 and you wanted to find out what that concentration was, it would be 10 to the minus 2.12. And that will give you that'll give you 7.5 times 10 to the minus 3. So like I said, I'm not going to go through all the numbers on this. You guys can do that when you're working on the homework. But it's these relationships that you're practicing using and getting comfortable with working in logs and working with antilogs and things like that. All right, well, let's talk a little bit more about acids, whether it's a strong acid, a weak acid, and what we mean by that. So here we have listed 7 strong acids: HCl, HBr, HI, nitric acid, sulfuric, chloric acid, perchloric. All we're saying when we're saying something is a strong acid is that it totally dissociates. When we talk about the weak acids, we'll see that in those cases, the acid doesn't fully dissociate. And what do we mean by dissociation? Dissociation means that the proton has been donated. The proton is no longer with that acid molecule. And so we see a generic expression here given, HA plus H2O going to H3O plus A minus. And so that HA is just a designation for a generic acid, a monoprotic acid. And so that proton transfers to the water. Okay, we get that hydronium ion. So our hydrogen ion concentration is as big as it can be, because all of the HA has dissociated into proton, H3O plus the anion, the A minus in this case we're calling it. So what that tells us though, is that for these strong acids, whatever the concentration of the acid that we made up, so like we weighed something out, for instance, was making up a solution, the hydrogen ion concentration is going to be the same concentration as what that was, because it fully dissociated. Strong bases is really the same concept, except now it's a base. And you think of some examples of strong bases: sodium hydroxide, potassium hydroxide. What those are telling us is that just as with that acid, when we put it in water, it donated all the protons. In strong bases, you put it into water and all the hydroxides are freed. So all the hydroxides are out there. Whatever the concentration of the material that you weighed out was, that solution, that's what the hydroxide concentration is going to be. There are some instances of where, like calcium hydroxide and things like that, where the cation is a positively 2 charge. And in that case, you get 2 hydroxide ions for every molecule of what you started with. So when we talk about weak acids, strong acids, we said it fully dissociates. So it goes from the acid with that proton, all the protons dissociate, leave that molecule, and now you've got a really high pH solution, relatively high pH solution. With a weak acid, some of the protons leave the parent acid, but not all of them. And the way we express this is once again with an equilibrium constant. But when we're talking about acids, we term it an acid dissociation constant, so Ka. It's the same type of equilibrium expression as that we've been talking about for, before break and then up now. So don't let the different terminology confuse you. It's the same thing. It's equilibrium is all, except we're just focused now on acids. And Ka, kind of like the dissociation constant for water in that, you typically talk about it in terms of pKa. And we'll talk about that a little bit later, but initially we won't. We'll keep it in the Ka form. But what this is really useful for, so acid dissociation constants are something that in the chemistry world are hugely important because it tells you how dissociated something is, and you can control that dissociation on these weak acids by doing some certain things in the reaction mixture. And so people are always interested to know acid dissociation constants. The larger the value of Ka, the stronger the acid. And that makes sense because we look at our expression, our equilibrium expression, products over reactants. If that number is big, then it tells me that a lot of H plus is in there. If a lot of H plus is in there, then it must have dissociated a lot. That's our definition of a strong acid. So the stronger the acid, the higher the Ka value. Here are just some weak acids. There's millions of these things out there, but here's just a few. And what you can get a feel for is just what some of those dissociation constants are. And so you see benzoic acid down at the bottom, and you see that's about 10 to the minus 5. So we know that that isn't dissociating a lot, right? That's a smaller number. Acetic acid, that's the acid that's in vinegar, okay? We see that's about 10 to the minus 5 as well for its acid dissociation constant. So it's not doing something like phenol down at the bottom. That one is technically an acid, but you can see its dissociation is 10 to the minus 10. So it's not dissociating much at all. So that's an acidic group, but it really doesn't, it's not a ready acid. So if you were trying to acidify something, you wouldn't necessarily use that. So once again, when we talk about strong and weak acids, all we're really saying is that strong acids completely dissociate. And dissociate means it goes to the ions. It goes to the proton, the cation, and it goes to whatever anion is associated with it. Weak acids just say that you have some dissociation like that, but it's not the whole thing. It's a portion of it. And that's where that Ka value helps us understand how much of dissociation did occur. And the more dissociation, the stronger the acid. Okay, so these relationships allow us to do some calculations. And these equilibrium calculations that we're going to do, we're going to be focused on pH in these types of calculations, but they're really no different than the calculations we did before, okay? You look at the equation, you see what the coefficients are, you then write those equilibrium expressions, and you plug stuff in. Except we're going to get a little surprise here in a little bit that actually makes it even a little easier than what we were doing before. So let's work through a couple examples here. The first one is, we're told the pH of a 0.1 solution of formic acid at 25 degrees is 2.38. And we want to calculate out what that acid dissociation constant is for formic acid. So we're told our equilibrium expression is hydrogen ion concentration times formate concentration divided by formic acid concentration. So in order to calculate it, we need the equilibrium concentrations for all these. Well, we were told the pH is 2.38, right? So that's telling us we can figure out what our equilibrium concentration is for the hydrogen ion. And we know from our stoichiometry that the hydrogen ion concentration is going to be the same as the formate concentration. So once we get that hydrogen ion concentration in a molarity units, because right now it's not in molarity, then we can have that, we can have the HCO minus, and then we can also use what our starting concentration of the formic was versus what it changes to help as well. So let's go ahead and do that. So let's do this first calculation to convert that pH value into a hydrogen ion concentration. And remember, we said, if we want to go back from pH or POH or any of the P functions back to what it came from, the concentration, it's 10 to minus whatever that number is. So in this case, it's 2.38. So it's 10 times 10 to the minus 2.38. That value is 4.2 times 10 to the minus 3. We know that hydrogen ion concentration, formate ion concentration are equal. So boom, we've got two constant equilibrium concentrations there. All we need to do now is figure out what this equilibrium concentration is on the bottom for the formic acid, and then we can solve for Ka. Okay, so we're going to set up our table, right? Just like we did for other equilibrium type of problems. We're going to set up our table. So we have our reactants and products across the top. Then on the left-hand side, we have what the concentrations were initially. So we started with 0.1 molar formic acid and nothing of the other. Then we had a change. That's that equilibrium, right? And so we just did our calculation since we were given a measured pH value. We calculated back to tell us what the hydronium ion, the hydrogen ion, and the formate anion concentrations were. That's that 4.2 times 10 to the minus 3. So that's the amount that was formed. So that amount must have reacted with the formic. And so we take 0.10 minus 4.2 times 10 to the minus 3, and we get 0.0958. But wait a second, let's take another look at this. If we think of our significant figures, we had two significant figures in our 0.10 concentration. So because we all love significant figures and we don't want to violate any of those rules, we're going to round this to the proper number of significant figures, which is 2. So if I take 0.0958 and round that to the two significant figures, what do I get? 0.10. Okay, that's interesting. Isn't that what we started with? Well, this is something that you'll see, and this is why I was saying these weak acid calculations are a little bit easier than the equilibrium calculations you did on the last quiz, for instance, because you don't get a large amount of dissociation. And because of that, a lot of times you can neglect the amount that dissociates. And what does that do? It keeps you from having to use the quadratic equation. So instead of 2 pages of math that you got to do, you've got maybe a quarter page of math to do. So you'll see an example in a little bit later this morning where we take that into account. So for here, you see we plug in those numbers, the 4.2 times 10 to the minus 3, they're both of those in the numerator, and then that 0.10 in the denominator, because we're good with our significant figures, and we're able to calculate out what Ka is. Okay, so let's think about that a little bit. You know, it seems weird to me that we said we used up some of the formic, but yet we had an equilibrium number that was the same as our initial number. That's kind of weird to me. So let's just see how weird that is and if we're really off base with that. Well, there's a calculation you can do that's called percent ionization. And so what that calculation is it's the proton concentration, so the H plus concentration at equilibrium divided by the initial acid concentration. So for the problem we just worked, we know that our initial acid concentration was 0.1 molar. So that goes in our denominator. Let's look what we said was our percent, what our hydrogen ion concentration was that we just solved for. That's that 4.2 times 10 to the minus 3 molar. And so we divide that 4.2 times 10 to the minus 3 molar divided by 0.1 molar. We want a percentage. So we do that math and then multiply by 100. And we see it's 4.2% ionization. So that's a pretty small amount of ionization, right? And that's one reason why you can kind of get by neglecting it in this problem. And sometimes maybe that's critical and you wouldn't want to neglect, and then you'd have to go through and use the quadratic equation. But a lot of times your starting concentration is so much bigger than what the amount of dissociation you get. And this percent ionization is pretty low. And so you can get by neglecting that and not having to subtract out and then get yourself involved with the quadratic equation. So when we first started talking about equilibrium, there was the one slide that I said, here are some rules of how you want to think about solving these problems. And if you're going to spend some time learning a slide, this would be one that I'd spend my time doing, because it really gives you a feel for the thought process that you need to have. So there's a similar slide here, and that's what I have up now. And I would suggest you spend some time looking at that slide as well. But what I hope you'll notice is it's pretty much the same slide. There's one difference down at the bottom, but in general, it's pretty much the same slide. So once again, we're going to write the chemical equation, okay? And that allows us, we want it balanced, it allows us to know what the stoichiometry of the reaction is. Then we write that equilibrium expression, okay? Then we set up our table with the initial, the change, the equilibrium concentration with reactants and products. We kind of set that table up again and fill that in. The one exception is if that amount that is dissociating looks like it's pretty small compared to what we started with, we can neglect that X and don't subtract that. And what that does is that takes us from going down a path of more complicated math. So we wouldn't have to use the quadratic equation. So let's do an example of what I'm talking about. So here we have 0.3 molar acetic acid, and we want to calculate the pH. So here's our acetic acid dissociation reaction. So it's acetic acid plus water, giving us hydronium ion plus acetate ion. We write our expression. So it's H3O plus times acetate divided by acetic acid. We don't include the water because that's a pure liquid. We go then and set up our table. We have our reactants and our products at the top there. And remember, this is all in molarity. And then we have initial concentration. We start out with 0.3 molar acetic acid, zeros for the products. And then we have a change in concentration. So some amount of the acetic acid dissociates. And so we'll define that amount as X. It's going to be X formed or X across the board. because the stoichiometry of the reaction tells us it's all 1 to 1 to 1. So we have minus X as the change for the acetic acid, then plus X for the change in hydrogen ions and acetate ions. And so then our equilibrium then values would be 0.30 minus X, then X and X. So looks like we're going to have a quadratic equation again. So let's go ahead and fill in our equilibrium expression. So it's X times X divided by 0.30 minus X. So if this was before spring break, we'd be getting ready to get a few extra pieces of paper out because we're going to go and break out the quadratic equation and start doing some algebra and doing all that. But because this is a weak acid, remember we talked a little earlier about looking at that acid table, and acetic acid was one of the weak acids. So what that tells us is that, well, it probably doesn't dissociate a lot. And so what we can do is if we assume that X, so the amount that it's going to dissociate, is a pretty small number compared to 0.3, then we can neglect in that denominator the minus X term. So then it just becomes X squared divided by 0.3 equals the constant, which we were told is 1.8 times 10 to the minus 5. And so another thing that I would say is remember I said that the Ka value is an indicator of how strong the acid is. We see here, we had the table that said acetic was a weak acid, but we also see a number here of 1.8 times 10 to the minus 5. So that's also an indicator that the hydrogen ion concentration isn't going to be a real big number because it's not, the dissociation constant is relatively low. So let's go ahead and finish the math. So if we solve this, X is 2.3 times 10 to the minus 3. We want to go and then find out, so that's our concentration. We want to find pH, so it'd be minus the log of this, and then the pH is 2.64. So by knowing that it's a weak acid, and we know that from the table, but also from seeing the Ka value being 10 to the minus 5, we know there's not going to be a lot of dissociation. And so we're probably okay neglecting that. And sure enough, if we see 2.3 times 10 to the minus 3, if we subtracted that from 0.30 and stuck to our significant figures, it wouldn't have changed. It would have been similar to the first one that we did. So it was a pretty good assumption to do that. So once again, strong acids, that hydrogen ion concentration is going to be pretty much the same as the initial concentration that you made. Weak acids, that equilibrium hydrogen ion concentration is going to be usually quite a bit less than the initial concentration of the acid. Okay, so in the acid world, there's something called polyprotic acids. So we talked about how for these acids definitions, you have to be able to donate a proton. Well, some molecules have the ability to donate more than one proton. And that, because it's got hydrogens that it can donate, that defines it as a polyprotic acid. The first one that it donates is often a lot easier to donate than the subsequent ones. And so if each of those protons that can be donated will have a Ka value associated with it. So it's not the same value for all the protons, they're different. And they come off in order like that, okay? If the Ka difference is 10 to the third or greater, then the pH will only depend on that first dissociation. If it's closer to that, then you start getting some overlap. But the rule of thumb is 10 to the third or greater difference, then you don't get that overlap. And so let's take a look at a couple examples here. So in this table, we have a bunch of different polyprotic acids. If we look at the first one, ascorbic, we see 10 to the minus 5, and then we see 10 to the minus 12. That's greater than that 10 to the minus 3 difference. So those are going to go pretty orderly. If we look down at citric acid, the third one down, we have 7.4 times 10 to the minus 4th. Then we have 10 to the minus 5th, 10 to the minus 7th. So citric acid has 3 donatable protons. And what you see is they're close together. So you start getting the second one donating protons while the first one still is, and you can even get some of the third ones donating. So if you wanted to work with that, you may have to have a little tighter pH control to limit what's being donated. So phosphoric is another common one, the H3PO4, and people will use that. You have nice separation there. You have -3, -8, -13. And so you can really, phosphoric acid is a real popular buffer. And one reason is you can dial it into 3 different pH ranges and control things pretty well there because you don't have overlap. The overlap's kind of a pain in the neck, to be honest. Okay, so the next part to talk about are bases. And I think we're going to stop there for today because I don't want to get partially through the base and then have to stop or something. So on Thursday, we'll pick up and we'll go through the base part and continue on from there. All right, well, thank you. See you Thursday.